and what we can expect for the future, also starting from what we're learning now. So if you can go to the next slide. Yeah, my outline is very simple. Very, very, very brief introduction about why supernova 1A cosmology is interesting, and then I'm going to talk about DES and Rubin. Yes. So if you go to the next slide, I think you have been talking for a week about transients and supernova 1A, and I'm sure you already touched on cosmology, so I'm not gonna kind of tell you how we do supernova cosmology, but I really like to start from this plot. This is from the desk science requirement document that was published a few years ago, and shows the different constraint on the dark energy equation of state, so W0 WA, for different probes. And all the probes that kind of LSST will explore. And as you can see, the supernovae are presented in the green contour, and as you can see, supernovae are one of the most complementary probes in this plot. And I really like this plot because it shows us that supernovae give really are extremely powerful when combined to other probes, and can really help us to kind of understand the nature of dark energy. Next slide, please. So now I'm gonna immediately dive into the dark energy survey and how we do supernova cosmology in DES. So here you see the kind of the footprint of the dark energy survey and the 10 supernova fields that DES identified to do supernova cosmology. Those are kind of marked with those little circles. And basically, DES monitored and repeatedly observed those 10 fields over 5 years. And this allowed us to discover thousands of supernovae 1A. And while the kind of DES imaging surveys was monitoring these supernovae 1A and measuring the light curves, the OSDES survey, next slide, was using the spectrograph on the Anglo-Australian telescope to measure supernova spectra and supernova host redshifts, and kind of offered that kind of allow us to get those extra spectroscopic information for those for these DES supernovae. So next slide. These kind of combined DES and OSDES surveys allowed us to start to do very competitive cosmology. And so the first cosmological results from DES are kind of summarized in these slides and were presented almost 3 years ago now. And so for this very first analysis, we used 100 low redshift supernovae. These are presented in orange here. And we combined them with roughly 207 supernovae from DES. These are supernovae that has been spectroscopically identified as 1As. So they are almost 100% supernovae 1As. And here you can see on the right, I put the Hubble diagram that we managed to build from these two combined samples. The Hubble diagram is redshift on the x-axis and supernova distances on the y-axis. And these redshift distance measurements allowed us to constrain cosmological parameters. And this is what I show on the plot on the left side. On the left side, I'm presenting the contours, the constraints on omega matter, the content of matter in the universe, and W, which is the dark energy equation of states. And then you can see from this plot, with these preliminary data sets, we managed to provide almost 6% constraint on W, and we show that for now we see a universe that is consistent with lambda CDM model, cosmological constant non-evolution. We don't see any evolution in the dark energy equation of state. So these results were great, and but what we actually see on this Hubble diagram and what we actually published 3 years ago uses just 10% of the data that DES has. And this is not only because in this analysis we included just the first 3 years of deaths, but more importantly, this is because each of these death supernovae that you see in this Hubble diagram required hours of telescope time in order to get a spectrum of the supernova and kind of confirm that that supernova was a 1A. If we relax the requirement of a spectrum of the supernova, we actually get a sample that is 10 times larger. And you can see this in the next slide. So this is the final death supernova sample. We call this the photometric supernova sample because we don't require this spectroscopic follow-up of the supernova. And for this sample, we have roughly 1,700 supernovae, likely supernovae 1A, that can be used for cosmology. We also kind of included in the low redshift sample an extra 150 supernovae coming from the foundation. So this is kind of the final one that you will see published in a few months in the final kind of death cosmological analysis. And it's an extremely powerful coming from like this great telescope, that great camera that Deacon was. Now, the statistical power of a sample like this is extremely good. Is a significant improvement compared to the death tree analysis that we published years ago. But this increase in statistics comes with some new challenges. And if you go to the next slide, I kind of, actually the next one, I kind of highlight this. As you might have seen from this Hubble diagram, there is kind of this population of outliers that wasn't in the 3-year Hubble diagram. These outliers are likely non-supernovae 1As. They have light curves that are very similar to 1As, but they're actually intrinsically fainter, and they're most probably core-collapse supernovae. These are not standardizable candles, so including them in our cosmological analysis can potentially significantly bias our cosmology. These, of course, if we had a spectroscopic confirmation of each of these events, we could identify them, but in this photometric sample, we don't have this extra information. So this source of systematic that we usually call contamination, of course, needs to be addressed when using this death final sample. And next slide, one of the ways we use to kind of control this contamination is using supernova photometric classifiers. I believe lots of people at this workshop have been working in some ways with photometric classification, and these are very interesting and it's a very one of the challenges when it comes to using photometric classifiers. Photometric classifiers need to be trained, need to be tested. And we need to somehow quantify cosmological measurements from the implementation are very good, but they're not perfect. So we need how bad they can affect our cosmology. One of the kind of ways to address all these questions and to test these classifiers is to use simulations. And this was kind of the first challenge that in DES we had to face. Like, do we have simulations that we can trust in order to train, test, classification algorithms and predict what biases on cosmology this can predict. So in the next couple of slides, I'm going to tell you all the work that went into these simulations and why we believe that now we can trust them. So next slide. I'm going to go step by step. So the first step in building the simulations was to consider a volume of the universe like the one that the Dark Energy Survey probed, and fill this volume of the universe with transients, in particular the transients we care mostly about for these analyses, which are supernovae 1A, peculiar supernovae 1A, and core collapse supernovae. And in order to do this, of course, we had to, well, first of all, use templates, set of templates that can model these transients. And we had to use some information about their intrinsic properties, their intrinsic luminosities, their rates, etc. Next, next slide, we had to kind of associate each of these transients to their host galaxies. And again, in order to do this, we had to publish measurements of supernova rates as a function of host galaxy properties. So we consider a complete sample of this and knowing the rates for each galaxy, and knowing the supernova rate for each galaxies, we kind of associate a supernova to a galaxy. The third and fourth steps, next slide, is to, once we have kind of simulated all the astrophysical components, supernovae and galaxies, we had to kind of simulate all the observational effects that comes from the fact that we have to observe this universe through the eyes of our telescopes. So first we apply the observational noise and detection efficiency associated with the imaging survey DES. And third and fourth, we have to apply also the selection efficiency that is associated to our spectroscopic redshift survey, which is also DES. These last two steps are very well kind of modeled, because we know very well, kind of we have tried to learn very well how our surveys work and how efficient they are. And the way these surveys were kind of conducted was such that a posteriori we could kind of determine very well, like how our targets were selected and how well our efficiency was as a function of the brightness of our supernovae and the brightness of our host galaxies. So this is kind of how our simulation, and I want to highlight that kind of the process that we try to follow is to kind of start from first principles, like what we know about the universe, about supernovae, about their host, and kind of try to forward model, like giving our knowledge, our astrophysical knowledge and instrumental knowledge of DES, like can we kind of reproduce like what we expect to see from DES. Now, in order to test whether our simulations are realistic, are correct, kind of the ultimate test is to compare these simulations to the data and see if what we simulated looks anything like data. And if you go to the next slide, I kind of try to show how this validation process worked. So here I show three panels. These are the observed distributions of redshift, host galaxy brightness, and residuals from the best fit cosmology. This is for real data, the DES data, and these are kind of three of the many kind of distributions that we checked in order to validate our simulations. So if our simulations are correct, in principle, the simulated distribution of redshift of the host galaxies and residuals should match like what we see. And if you go to the next slide, I show you what our simulations are kind of predicting these redshifts, those galaxy and residuals distribution to be. I don't see the next slide, but maybe we switched. Okay, here we go. Here you see in gray all simulated supernovae. In red, I highlighted the contamination, the non-one observation and simulation is remarkable. And I want to really highlight that in our simulations, nothing was like tuned to kind of produce this match distribution histograms. These, as I said, are distributions. I've spent 3 years of my PhD in a sample that only has supernovae 1As. The residuals from the best fit cosmology should just look like one single bump, very symmetric. But if your sample is contaminated, one of the kind of most peculiar signs of the presence of contamination is that you have this kind of second bump of like faint core collapse that have faint, so positive Hubble residuals. Using our simulations, we kind of predicted this contamination to be between 6 to 8% of the sample before we apply some light graphite quality cuts. And here I want to highlight that the fact that we cannot match these two bumps is kind of a big deal, and it's also a very good sign that we kind of understand the contamination that is on our sample. We model the correctly, and we can trust these simulations to kind of be realistic enough to train, test our classifiers. So this was kind of our first result, and the kind of the first step that allowed us to be all our subsequent analyses that I'm going to present in the next few slides. So please interrupt me. As you can imagine, there are many ways, there are many choices that goes into measuring core collapse, simulating core collapse in Urbana-Champaign.
Maria, I'm afraid your audio's been cutting out a lot.
So I still see the previous slide, but I believe maybe it's just my Wi-Fi is very slow. Hello?
Maria, you've been cutting out a lot audio-wise. I have moved to the next slide, but I'm not sure it's updated yet on your screen.
Yeah, let me thank you as well, the other speakers. And sorry, apologies for the technical issues. So I hope this time it goes better, but let's see. So I think I left my talk at kind of this discussion about simulating contamination in the dark energy survey. And I was showing this histogram of the distribution of the residuals from the best fit cosmology. The two bumps are that you can see in this histogram corresponds to one, the supernova 1A, which are distributed around residual 0, and the second bump is kind of the contamination. So this fraction of non-1A supernovae that are intrinsically fainter, and therefore they appear as outliers in the Hubble diagram. And I was mentioning that one of the first challenges for that was to try to model that source contamination, and we did this testing different core collapse contaminants templates and different luminosity functions, different assumptions on dust, and the kind of colored histograms that you see in the plot show you how these different assumptions change the contamination in our Hubble diagram. After generating these different variants of core collapse contamination, if you go to the next slide, we used kind of these these different ways of simulating contaminants to train and test different mathematical classifiers. And here I list some: supernova that Anais developed and that Rebecca talked about, SCONE that Helen Q at UPenn developed and published last year, and another random forest classifier we developed internally. These are all machine learning classifiers. They are kind of the best on the market, and that's what we wanted to implement for DES. And we use our simulations and our different versions of CoreCollab simulations to train and test these tools, and to apply them to the DES data. These classification algorithms provide for each supernova simulated or observed a probability for that event of being a 1A. And this can be plugged into kind of the likelihood that is used to measure, basically to constrain cosmology. We kind of stress tested all these algorithms in many different ways. And the bottom line, let's say, of this big analysis was that the biases of cosmology, in particular the biases that we see on the Carnegie equation of state parameter W, are significantly smaller than the statistical uncertainties that we have for DES. This is kind of stated in the next slide. And this was a very important result. It took lots of simulations, lots of kind of validating the simulations, validating of the algorithms. And this was published in 2 papers that were accepted in 2021, 2022. And if you want to know the details of how kind of we came to the conclusions that really contamination has an effect that is subdominant compared to the statistical uncertainty that we have in DES, I invite you to go and look at those papers. If you go to the next slide, now I want to kind of try to put these contamination issues into into kind of the big picture for DES. And I would like to show you today, like, what are the most important systematics that are affecting the DES analysis, and what kind of cosmological constraints we expect from DES. So here I show a plot from the latest supernova cosmological analysis published for a sample that is affected by contamination, so a photometric sample. This analysis was published by David Jones using the PanStar data. And as you can see, he made this very beautiful pie chart to show the contribution of each different systematics in the analysis. And if you see the kind of the yellow slice was the CoreCollab contamination, and other slices showed different issues like bias corrections, calibration, Milky Way correction, light curve fitting, etc. We wanted to kind of keep this way of visualizing how systematics affect this kind of measurements. But if you go to the next slide, we kind of switch from pie charts to bars. So we started making these plots where you have next to each other a bar that shows you the contribution of the statistical uncertainty on W. Here we are focusing on W as the cosmological quantity that we want to constrain as tightly as we can. So we compare the statistical uncertainty to the systematics and show the different contribution of the systematics. So for PanStar, I kind of reproduced this double bar plot, and I showed that the statistical contribution was kind of almost equivalent to the systematics. If you go to the next slide, I show the same plot for DES. So as you can see, since we have a larger sample, both at high redshift, DES is slightly larger than PanStar, and at lower redshift, we included more samples. So our statistical uncertainties are significantly smaller, and also our systematic uncertainties are smaller. And in this vertical bar, I show you in different colors the different contributions of different sources of systematics. And From the pie chart that David Jones published for Pan-STAR to what we see now, there are significant differences that I would like to comment now. First of all, when we implement these machine learning classifiers that I was mentioning earlier, and we implement these different ways of simulating contamination, we see that the contribution of core collapse contamination to the systematic uncertainties is incredibly small. That's kind of the very thin red slice in my systematic uncertainty vertical bar. There are other systematics that are way more kind of critical for our analysis. And of course, the two that kind of probably are the most evident ones are the one related to intrinsic supernova properties. So how do we model the intrinsic supernova properties in our simulations, and how this affects how we calculate bias corrections for our sample. And the other, and this is kind of the darkish blue bit. And then you see light curve modeling and calibration, which is a dark greenish bit of our systematic error budget, are the two kind of main systematics in our analysis. Of course, the final uncertainties on W will be the combination, the sum quadrature of the two. So that will get an uncertainty on W that is expected to be below 0.035 once we include a CNV prior. Next slide. Since kind of this error budget showed you that studying intrinsic supernova 1A properties is kind of one of the major challenges that we're facing now, I wanted to just spend one slide mentioning what are these intrinsic supernova properties. And I think now the main ingredients that we're working on are dust, and how dust affects supernova 1A brightness, and in particular how dust in different how different properties of dust in different host galaxies can kind of explain some of the correlations that we see between supernova 1A brightness and host properties. And then there is lots of work going on in terms of trying to forward model how supernova progenitor age correlations with supernova properties like stretch can kind of also modify the way we model intrinsic properties of supernova 1A, and we generate bias corrections. Now, I'm not going to spend lots of time on this, but I really invite you to kind of look at these references that I put in the slide, the work published by Dylan Brown and then Skolnick 2 years ago, and the work published by another grad school at Duke, Brody Popovich. These are all about how we measure, how we model these dust properties in supernova 1A. And on the other side, on the kind of more progenitor age side, I invite you to look at this work just published by Philip Weisman and Lisa Kelsey. These are all great references, and our analysis on how we model these intrinsic properties of supernova 1A, they heavily rely on this analysis. So I invite you to take a look at them if you want to learn more. So next slide. So stay tuned. The message on the desk side is stay tuned, because in the next month we are planning to kind of get to the final cosmological analysis and publish our results. I think before switching to LSST and kind of conclude my talk looking at the future, I want to kind of give summarize kind of what are the lessons that we're learning in DES, and then I think it's very important to keep in mind while we prepare for LSST. So if you go to the next slide, I kind of try to build a series of bullet points of the things that I think has been very interesting for the DES analysis, and we should keep in mind for LSST. The first one is that contamination, especially now in the machine learning era, seems to be kind of not a second order problem somehow. Here in this plot that I didn't comment before, but in this plot I was showing the contours, the gray contours, which are contours estimated from a pure supernova 1A sample that has the properties of DES, while the red contours show you why if I add contamination to that sample and I implement photometric classifiers and I analyze that sample, including the fact that that sample might be contaminated. And as you can see, the gray and the red contours are almost the same. Like when we implement those classification tools, those very powerful classification tools, and we plug probabilities into our cosmological fit, the biases on contours are really subdominant compared to our statistical uncertainties. So that's one of the first lessons that we have learned. Next slide. The second lesson we learned is that having simulations that can robustly measure, model your survey is extremely important. And these simulations cannot be built unless we have a very well-known set of selection effects, selection criteria when it comes to determining our samples. Both on the side of the imaging survey, for DES, we have a very well characterized detection efficiency of the survey, and more importantly, when it comes to spectroscopic follow-up. Planning a spectroscopic follow-up that heavily relies on human kind of decisions is the worst that we could do for LSST, because that's something that is absolutely impossible to model. So we need to really be careful on how we plan that spectroscopic follow-up. Next point, well, I kind of, the next slide, sorry. The error badges I just showed kind of screams at the message, we need to understand supernova intrinsic properties. And we need to make sure we understand those intrinsic properties. And most importantly, we need to understand if a photometric sample, a contaminated sample, is good enough to kind of to understand better, to make some steps forward in understanding supernova intrinsic properties. When it comes to contamination, of course, we always think about, okay, what is the bias on cosmology? What is the bias on W from core collapse contaminants? And that's, of course, part of the problem. But another kind of interesting question that is still yet to be fully answered is, from a contaminated sample, can you learn more about the astrophysics of supernovae 1A, or is that contamination kind of undermining our ability to learn more about supernova and astrophysics? And then last point, and this I didn't really talk about, second following slide, we didn't talk a lot about low Z, combining high Z with low Z samples, but that's another important important element for these kind of measurements. Can you still hear me? Yeah.
Sorry, Maria, we lost
Hello?
you very briefly there, but you're back now.
Ah, okay, perfect. Very briefly. Okay. Oh, I apologize. So, am I back? Can I continue?
Yes, continue, please.
Okay, perfect. So now, I believe we're at slide 30. Now I kind of want to go to the next bit of my talk. I'm sure, I promise I'll be very quick. So everything I showed you for that, and especially the kind of simulations we built and all the forward modeling that I'm implementing for that, that could be implemented.
Maria, could you just hang on 1 second? Apparently in that slight disconnection, we also lost you on Zoom.
Oh, okay. But the audio is still
we're just
working.
sharing your slides again, because apparently it was just disconnected when whatever that.
Oh, okay. Okay, sure.
Please continue.
So, okay, so this kind of simulation framework that I've been talking a lot about, and that has been kind of the foundations of our analysis for that, can be very easily applied to LSST and spectroscopic follow-up surveys like TIDES. And if you go to the following slide, basically all we need to do is to apply the same framework, but instead of implementing the DES, detection efficiency, and cadence, we use the better Rubin one. And instead of modeling the spectroscopic follow-up of OSDES, we, with the help of Christopher Meyer, modeled the spectroscopic follow-up of tides. This was a very powerful kind of exercise. And if you go to the following slide, it allowed us to kind of build some predictions of what kind of cosmology we expect to do with LSST. This is the gigantic Hubble diagram that we expect in the next to see, hopefully, in 5 to 10 years. And if you go to the following slide, it includes roughly 30,000 supernovae 1A that will be spectroscopically identified as 1A from tides, using tide spectra. And following slide, we have exactly as this, we have another sample of, in this case, 20,000 supernovae, for which we won't have a spectroscopic confirmation of the type, but we will have the redshift information from the host. We also predict, that's another very important point to keep in mind, that we will have thousands of low redshift supernovae that can allow us to kind of anchor these massive high redshift samples that we expect from LSST. So using these simulations, we kind of try to run a cosmological analysis from end to end. And next slide, we try to measure cosmological contours. And here I'll show you in particular the omega matter and W contours for different LSST plus tide samples, the one that used only spectroscopically confirmed 1As, the one that used a contaminated photometric sample of 1As, and the two contours combined. And since I've been talking a lot about systematics and how
Maria, could we finish up in a couple of minutes, please?
Yeah, sure. Here I show kind of the two contours, statistical and systematics. And if you go to the next slide, actually the following one, you can see that I have this kind of comparison between statistical and systematic uncertainties. And this is probably the kind of optimistic error budget, but it showed us that if we kind of if the control systematic that we expect to have when LSST will be on is correct, we shouldn't be systematic dominated. So I don't want to steal more time actually from the speakers of the session. So I'm gonna just finish here. I had some extra slides on how to do cosmology using peculiar velocities in the LSST era and some simulations that we run on that. But I'm happy to kind of upload the slides whenever on the website, and people I'm sure can ask me questions if they want to know more about this different way of using supernovae 1A from LSST and still do cosmology. But yeah, I would prefer to finish here rather than stealing more time from the rest of the session. I don't know if there's time for questions. Yeah.
I think what we might do is have people that want to talk more with you. And since there's so much more to talk about, I think we should have questions on Slack in your case. But let's all thank Maria. I mean, any disruption to a talk is always stressful. And to come back like you have and pick it up is really, and persevere is really quite amazing. So thank you so much for presenting remotely on your vacation, Maria.
Thank you.
And I do hope you'll be able to interact with the audience over Slack.
Yeah, sure. Send me any question, and I'll be very happy to reply.